Hello friends, welcome to DCBA Online. This is yet another lecture for moment distribution method, and this is continuation of my previous lecture in which we solved problem type 2. This is problem type 3. Uh, the distinct feature of this type is that it has an overhang. Okay, and how to solve problems having overhangs using moment distribution method is uh, shown here. Okay, it has an overhang as well as pin joint. Okay, now I've solved this problem using Carney's method as well, the link of which would be given in the description. You can check that out as well, and you can match the answers later on. Okay, now step 1 is finding fixed end moments. If you have referred to my previous tutorials, even of Carney's method, I've showed there how to find fixed end moments, and basically I've just shown all the formulas that are required for finding fixed end moments, and you can memorize them or you can just write them anywhere. And here we require only two types of formulas basically. That is, one is for point load and another is for a UDL. Okay, so let us start with fixed end moments. First is MFAB, which is minus WAB square by L square, and minus is because I have taken anti-clockwise as negative. That is my sign convention. Your sign convention could be different as well, but you have to follow that sign convention throughout the sum. Okay, so this is minus WAB square by L square, where W is 60, A is 2, B is 2 again, and L is 2 plus 2 4. Okay, so it is minus 30 kilonewton meter. MFB is WA square B by L square, where again WA and B stand for same as for that of MFAB, that is W 60, A 2, B 2, and L 4. This is plus 30 kilonewton meter because this is of clockwise nature. Okay, MFBA. MFBC is minus WL square by 12, where W is 40, L is 4, and MFPC is minus 53.333. MFCB is plus WL square by 12, and it is equal to plus 53.333. MFCD is minus WAB square by L square, again the same formula, and it is equal to, where W is 30, A is 2 meters, B is 1 meter, and L is 2 plus 1, that is 3. So MFCD is minus 6.6667 kilonewton meter. MFDC is plus WA square B by L square, where W is 30, A is 2, B is 1, L is 3, and it is equal to plus 13.333 kilonewton meter. MFDE is the overhang is basically like a cantilever, and the fixed end moment here would be simply a cantilever moment, that is W into L, where W is 15 and L is the overhang length, that is 0.6, which is equal to minus 9. Why minus? Because it would be a negative, since this 15 kilonewton would try to hog my beam. Okay, there would be a hogging moment. I'm sorry, there would be a hogging type of deflection. Okay, so to counteract this, the support has to provide an anti-clockwise moment of minus 9 kilonewton meter. So these are fixed end moments, and step 1 is completed. Let us move on to step 2, that is finding the distribution factor. Okay, so the distribution factor we can find in a tabulated manner, and the first column is basically of joint, and we have to write only those joints which are intermediate joints. Okay, so in our case, A and D are my end joints and B and C are my intermediate joints. So why they are called intermediate joints? Because they connect two or more members. Okay, so first column is joint, second is the members that are connected by my joint B, okay, or for that matter joint C, and B connects BA and BC, C connects CB and CD. Third is relative stiffness. The relative stiffness is as if you have gone through my previous video tutorials, I have uh, mentioned the formulas for finding relative stiffness for different types of end conditions. Okay, so I would just suggest you that you go through those tutorials, or you might even get it anywhere on the enter it. Okay, so relative stiffness for BA, since my A is a fixed end, it is EI by L. BC, again C, we are considering it to be fixed because that is a primary assumption for solving any type of indeterminate structure, that all the intermediate joints are considered to be fixed. Okay, so since B is my intermediate joint, B and C, I am considering them to be fixed. A and D are my end joints. Okay, so since C is fixed, it is EI by L. CB, okay, CB is again B is the far off end and B is fixed, so CB is EI by L again. And CD, since D is the far off end for CD and D is a pin joint, so the relative stiffness is 3 by 4 EI by L. Okay, now I'll substitute everything in these formulas. E is same for all the segments, segment AB, BC and CD and DE as well. Okay, but I is changing. I for AB and BC is same, but for CD it is 2I. So let us substitute it as it is. EI by 4 is for BA, EI by 4 for BC again, since L is 4 for both the segments. CB is also EI by 4 and CD is 3 by 4 E into 2I by L. L is 3. Okay, the total relative stiffness is for any joint is summation of the relative stiffness for the members that the joint connects. Okay, so total relative stiffness, if I just sum them up, I get EI by 2, and for C, if I sum these up, I get 3 by 4 EI. Alright, and the distribution factor, that is what we have to find. Distribution factor is equal to a relative stiffness of that member divided by total relative stiffness. So it is equal to 0.5. If I divide this by this, I get 0.5. Again, if I divide this by this, I get 0.5 for BC. If I divide EI by 4 to 3 by 4 EI, I get 1 by 3 for CB, and for CD I get 2 by 3. Okay, so distribution factor step is done, step 2 is done. Let us move to step 3. Okay, this is our final step, that is of moment distribution. I've just written here all the I've drawn it, redrawn my beam again. Okay, and here this is A, B, C, D and E. I'm sorry the names are not visible, but it's A, B, C, D and E. So what I have to do is I have to basically draw a box around my intermediate supports. Since B and C were my intermediate supports, I had to draw a box here. Alright, and now I have to fill these boxes. So the upper portion of the boxes would be filled by the distribution factors, which we just found. Okay, and for BA it was 0.5, for BC it was 0.5, for CB it was 1 by 3, and for CD it was 2 by 3. And the lower boxes would be filled by fixed end moments. So for MFAB was minus 30, MFBA plus 30, MFBC minus 53.333, MFCB plus 53.333, MFCD is minus 6.667, MFDC oh, okay. So MFDC is plus 13.333 and MFDE is minus 9. Okay, now I'll just show you one concept of moment distribution method. I have even shown this concept in my previous video tutorials. If you have already learned this, you can skip it, but do not skip the whole thing. There's a concept of overhang as well. Okay, so let me start with this concept. Basically, just a minute. Okay, basically you can see this is joint B, and 30 and minus 53.333 are the fixed end moments that are around my joint B. Okay, and the nature of these moments is this is clockwise and this is anti-clockwise. So if I just sum it up, because these two are adjacent to each other, you can sum them up and you will get a resultant moment that will be acting on the joint B, and it would be minus 23.333, and it is anti-clockwise and which has rotated my joint. Okay, so as structural engineers, you cannot permit rotation of joints, thus we have to counteract it. So how to counteract this? This is minus 23.333 anti-clockwise. To counteract it, we can provide a plus 23.333 that is in the clockwise direction, and it will get straight again. Okay, so the rotation is gone basically. Now from where does this 23.333 comes? It comes from the inner strength of the beam itself. Okay, now beam can be made up of any material, and any material or every material has its own strength, be it steel, concrete, timber. Okay, every material has its own strength, and from its own strength the beam provides a resistive of moment of 23.333 to counteract this moment. Okay, because even the beam doesn't want to get deflected. Basically rotation meaning it has got deflected, and no structure wants to get deflected. Okay, so what happens is this 23.333 is basically given by BA and BC, so there is some contribution of this moment by BA and some contribution of this moment by BC, and how much contribution is done by BA and BC is given by the distribution factors of BA and BC. So basically I'll just split them up. I multiply these by the respective distribution factors, and this is contribution by BA and this is contribution by BC. I hope it is very clear, the concept of moment distribution. Okay, now these are the values. These values written in red are what we require for the calculation in moment distribution. Okay, okay, let us move ahead. Now I've drawn this joint D. Okay, and as you can see here, the moment is 13.333 and minus 9. So if you see this joint D is basically unbalanced, since there are two moments adjacent to it and which are not equal in magnitude, and which are of also different nature, right? This is clockwise and this is anti-clockwise. Okay, so basically what we have to do is, in load balancing we have to make this moment equal to plus 9 so that it is balanced by minus 9. Plus 9 and minus 9 gets balanced. Okay, so the net result would be 0. As you saw here, it was 30 and minus 53.333, so it was giving a net result of minus 23.333. We don't want that to happen here, since this is a pin joint and pin joint cannot take you might be knowing that pin joint cannot take any moment. Okay, it directly deflects. So if there is even a moment of 1 kilonewton meter on this joint, it will deflect my beam, or it will rotate my beam at that support. Okay, so I want to balance my joint D, and how to do this? First I'll make this 0 by providing a, see, you can see here it has now got displaced because there is an unbalanced moment. So what I'll do, I'll make this 0 by providing minus 13.333. okay, now this minus 13.333, as in this case it was given by the beam itself. In this case the sub joint, pin joint, does not have any strength to provide this moment. Okay, so this moment as structural engineer we provide it, and when we provide it we have to carry over it. I'm sorry, this has to be minus 6.667. That's my mistake, I'm really sorry. Okay, this has to be half, so minus 13.333 divided by 2, it should be minus 6.667, and this has become now 0. But what is the end result that I want here? I want here plus 9, so I'll just add plus 9 again and I'll carry over it again. So plus 9 into half will give me 4.5, and when I sum it up, if I sum this up, I get it as, see, now it has become straight, plus 9 and minus 9. Now there is no unbalanced moment here, that is the reason my beam has become straight again, and it is plus 9 minus 9. This is what we wanted and this is what we achieved. Okay, so I hope you are very clear with the load balancing concept. Okay, I'm sorry, moment balancing concept. So let us move to the next step, which is iteration of moment of the beams. Okay, so I've drawn here the beam again with distribution factors and fixed end moments, and let us first of all balance this joint as we saw previously. We'll do it quickly. I'll provide minus 13.333 so as to make it 0, and then I'll add plus 9 again. So see, now I've written it correct. When you take it to the next support, immediate support, it becomes half. So it is minus 6.667, and then when I add plus 9, it becomes plus 4.5. Okay, now I'll just sum it up and let's see. Now this is minus 38 becomes minus 30, 30 is 30, minus 53.333 becomes minus 53.333. This comes down and I have to add these up. Okay, and when I add these up I get minus 8.833, and when I add these up I get plus 9 and minus 9. So our joint D, pin joint D, is balanced and we will not disturb it anymore. Okay, once we have balanced it, we won't disturb it anymore. So these are the moments with which you have to do further iterations. So let us start with our first iteration, and this first step of our iteration is balancing of moment. As we saw earlier, that 30 and minus 53.333 was giving a resultant moment of minus 23.333, and to counteract it my beam was providing a moment of plus 23.333. So my beam was balancing it by this moment. So balancing step basically means writing these moments. Okay, again here 53.333 minus 8.333 is will give me plus 44.5, and to balance that plus 44.5 my beam will provide a anti-clockwise moment of minus 44.5. Okay, so this is my balancing concept. Of first iteration we have done balancing. The second step of first iteration is distribution. Okay, now we just have to distribute it. Here I have written 0 because there is nothing to balance here, and thus since there is nothing to balance here, it becomes 0. Okay, distribution of this is basically how much contribution is done by BA and BC. So how to find that? We have to multiply this by the respective distribution factors. We get 11.667 and again 11.667. Again we have to multiply this value by 1 by 3 and to get here, and this value by 1 by 3 to get contribution of CD. So this is contribution of CB and this is contribution of CD. Okay, and we won't disturb this joint. Next step of iteration is carryover. Carryover is same thing as you did here. You just have to carry over it. 0 becomes 0. While carrying over it, you have to multiply it by half. So 11.667 becomes 5.833, half of it. Again carry over here in the next segment. Now carryover has to be done in every segment. Okay, segment AB, segment BC, and segment CD. Now I won't carrying over this value here because I don't want to disturb this. Alright, and since there is nothing to carry over from here, I'll just write 0 because there is nothing here, no value here, so there is 0. Okay, so carryover step is over, and this is our first iteration including three steps: balancing, distribution, and carryover. First iteration is over. Now let us go to next iteration, second iteration, which has its first step as balancing, and now these are my unbalanced moments, 0 and minus 7.4167, and thus to counteract this my beam has to provide a clockwise moment of 7.4167, and here my beam has to provide an anti-clockwise moment of minus 5.833 to balance this unbalanced moment. Okay, next step is distribution. So again I multiply this by its distributing factor. I get as 3.7083 and again 3.7083, and for C I multiply this by its respective distribution factor. Again I get these values, Third step is carryover. So I carry over it as I've shown earlier. This will come here, this will come here, and it will be halved. Okay, and here again 0. So we have to continue this iteration process till we get distribution value or carryover value as very less. Okay, now we can see distribution value is 3.7083, which is quite significant. It is not less. By less I mean that it has to be in the range of 0.01 or 0.04. Okay, so let us start the next iteration. The first step is again balancing. We balance this unbalanced moment. Again here we balance the unbalanced moment. Next step is distribution. I multiply it by its respective distribution factor. Same thing here. Third is carryover. We carry over it. Okay, and here again 0. Now even if we see these values, these are not less. Okay, 0.486 is quite a high value, so we'll have to do another iteration now. And the first step of our iteration is balancing the moment. So we balance these moments. Again we have to follow the same procedure as we followed earlier. Next step is distribution of the moments. We multiply by the respective distribution factors. Third is carryover moment. Okay, so as you can see now, my carryover values are very less, and we can actually stop the iterations. So we have done here 4 iterations, but there is one very important thing that you have to remember, that you cannot stop your iteration at carryover step. Okay, you have to always stop your iteration at distribution step. So you could have stopped your iteration on this distribution step as well, but I recommend you that you do at least 4 to 5 iterations, and only then, when you see that these values are quite less, only then you stop your iterations. And even after these iterations, you will have to do again one more iteration. Okay, and you have to end it on the distribution step. So your moment distribution always ends on distribution step. So actually in our case 4 iterations were enough, but since it was ending on the carryover step, I had to do another iteration and had to end it on the distribution step. Now basically our iteration process is over, and we just have to sum it up to get the final moments. So let us sum it up here. So we'll add all the vertical values right from this -30 till this 0, and we get this moment. Again we'll add all the vertical values. You should add these values. Okay, these are distribution factors. You only need to add the moments, and you get it as 46.0359. Here you get it as -46.0359 plus 43.8385 minus 43.8385 and plus 9 minus 9. So you see all the joints are balanced here. They have equal moments on both the sides, but different in magnitude. So what you can infer from this is that since they are different in signs, different in natures, but of equal magnitudes, so they won't cause any external moment now. External moment on the joint to rotate it. Basically they are balanced, so they should be equal and opposite in nature. This is our final moment, and thus we have successfully analyzed our beam with an overhang. You can check this beam with the one that I have solved with Kani's method, and I'll provide the link in the description. Thank you so much.